Welcome. This is SCA's webinar today with Dr. Ursula Hammes. She'll be talking about Mudrock sedimentology on unconventional shale reservoirs, suspension settling, gravity flow, or current transport. And I'm your MC for the day. I'm Susan Howes. Before we start our presentation, we'd like to ask our questions for demographics. So please tell us what's your primary discipline. We'd like to see who we have signed on today. Looks like we have a good attendance and looks like a great group. Almost everyone has voted. Very close, so last chance to vote. So here we go. I'm going to share the results. It looks like we have a strong contingency from geoscience, 85%, and some representation from other groups as well. So thanks for that. We have one more question. And so this question relates to your experience. How many years of full-time experience do you have in the upstream oil and gas industry? And again, our votes are starting to come in. This gives us a chance to see who's signed in today and tailor the presentation accordingly. Almost everyone has voted, so I'll go ahead and share those results. Again, it looks like we have a good spectrum of different levels of participation. There's a few in each group, kind of a bimodal distribution with 29% in the mid-career and 29% in the late career group. So thanks very much for that. So I'm going to go ahead and share some slides here. And again, this is a presentation today that's brought to you by SCA. And we're doing this presentation as a sample of some of the material that Dr. Hammes includes in her workshop that she teaches for SCA. And so as an introduction here, Dr. Hammes has been recently an adjunct professor at Texas A&M. She's also president of her own consulting firm. She received her early education in University of Erlangen in Germany and her PhD at CU Boulder. And her specialty is in carbonate depositional environments, stratigraphy and carbonate diagenesis and rock-water interactions. Dr. Hammes and I worked together when we were both at Anadarko. She's also done consulting for Marathon and Statoil. Her research includes the Gulf of Mexico. She's worked for the University of Potsdam, Germany, and also the Bureau of Economic Geology at UT Austin. She's a past president of the Gulf Coast section of the Society for Sedimentary Geology. She's associate editor for an APG bulletin on shale liquids and gas committee chair for the Energy Mineral Division of APG. Ursula is an expert in mud rock shale analysis from around the world, and she'll talk a little bit about the nanoscale sequence stratigraphy of carbonates and siliciclastics. As I mentioned, she teaches core workshops for SCA. She also offers short courses in a number of different topics as well. So this is the workshop that she'll be teaching for SCA in January, Shale Reservoir Core Workshop, January 15th through 17th. And if you'd like to sign up, you can contact us to come to this class in Houston in January, or we can set it up in your in-house courses as well. SCA offers consulting, direct hire services. We conduct projects and studies, and we also offer training. So without further ado, I'm going to pass the presentation rights to Ursula. And Ursula, it's all yours.
Okay, welcome to my first webinar. I think it's very exciting, and I'm very excited to present some of the workshop that I'm going to teach in January for SCA to you. And maybe some of you have worked in Mudrock sedimentology, worked in Mudrock identifying sedimentologic features in Mudrocks before, but some of you might not have. And you know, the conventional thinking of shales was all the mud was just settled out of suspension. But but maybe there's some more that we can see in those mudrocks. Maybe there were like gravity flows or current transport. So here is just your current sedimentologic thinking of your sedimentary processes. You know, there are composed of transportation and deposition of sediments. These are basically your external influences. And the parameters that determine that are current flows, the flow direction, different type of sediments, and the duration. So consequently, those sedimentary features are visible through grain size and sorting contrast. And then we have a suspension settling of the finer sediments. Now here is a beautiful cross-bedded sandstone from the Devonian sandstone in Ireland. It's easy to see, right? You can see the cross-bedding right here. Beautiful trough cross-beds right there, right there. So what do we see in the core sample, in the shale core? It's gray, dark gray. You think you don't see a lot of features in there. I think you just have to look a little harder and really see where you are, in which kind of depositional environment you are. So here in sedimentology, the sedimentology in mudrocks is determined by more fine-grained sediments, extremely fine-grained sediments, very fine-grained sediments. And usually they're deposited in a low-energy distal settings. And we can see those distal sedimentation is dominated by hemipelagic and pelagic processes. We usually get a decreased contribution of terrigenous sediments and an increased contribution of oceanic sediments. And some of the terrigenous sedimentation is dominantly point sourced. So how do we identify any variations in mudrocks? This one here, for example, is a core photograph of an Haynesville core from Petrahawk over in Louisiana. And we can actually see a few features in there. We have generally very finely laminated sediments. You actually can identify, if you look closer, some slump features in there. How did they get there? We can see some bioturbation right in there. And then generally a lot of laminations, finely laminated mudstones right in here. Some color variations of calcitic fractures, horizontal fractures, maybe some inoceramide, some bivalve shells. But that's pretty much all we can see in this core. But if we can always look closely and identify how these slump features got there. So if you look at a Mudrock facies and sequence model, we have a proximal setting and a distal setting. And we have mudrocks in both settings, more the proximal, maybe like the slope settings right here. These are organic rich mudrocks on the slope. Or the distal settings, we have organic rich mudrocks in the basin. So you have to keep that in mind, your settings, where you are on the shelf. Are you closer to the shelf? Are you further away on the shelf? So here are features that we see more in the proximal mudrocks, for example, along the slope. They are interbedded with shallow water to terrestrial facies. We can also have a progradation and retrogradation, and that we can actually define. We can see some coarser grained sediments coming in and finer grained sediments coming out. These may be due to eustatic control, a tectonic control, or climate control. So the typical mudrock depositional controls in these proximal settings are fluvial deltaic systems. So for example, in the Eagle Ford, if you're familiar with the Eagle Ford at all, we have the woodbine sediments that are actually interfingering with some of the Eagle Ford sediments and actually transporting some of the fines, the terrestrial fines, into the Eagle Ford depositional environment. We have waves and currents that may be influencing your deposition of the mud rocks. Storm influences, we can see coarser grained clasts, be it bioclasts or interclasts or intraclasts that are visible within your sediments. And then you see your shoreline progradation and retrogradation. Now, as we go further distal into in the distal realm, in the deeper water environments, doesn't have to necessarily be very deep water, but just quiet water, I would say, we come into a more hemipelagic setting. And that can be, the sediments here can be influenced, can be both terrigenous and marine, or a mixture of that. And you know, it's important that you know that, because that influences your organic matter type. The terrigenous material is transported to basins, oftentimes as aeolian dust or turbid nepheloid flows, some turbidites. Your hemipelagic setting, hemipelagic sediments, you get marine snow. These are little floccules of organics and skeletal maybe materials like coccoliths, calcispheres that are raining down just like snow into the basin, and you can sometimes see these floccules. And then you have biological productivity that can be present or not, depending whether you have an anoxic setting or an oxic setting. We also oftentimes see density flow, and then also have bottom current redeposition. For example, contour currents, they've been observed in the recent environments, for example, in the Maldives. We have storms or internal waves that are making up your depositional environment. So Jürgen Schieber from the University of Indiana, he's published quite a bit on and does a lot of research on sedimentological principles in fine-grained sediments using a flume deposit. And he came across this quote from Sorby, 1908, that's 110 years ago. And I cannot read this here because it's my screen is in the way. Oh, here we go. Possibly many may think that the deposition and consolidation of fine-grained mud must be a very simple matter, and the results are of little interest. However, when carefully studied experimentally, it is soon found to be so complex a question, and the results dependent on so many variable conditions, that one might feel inclined to abandon the inquiry. Were it not that so much of the history of our rocks appears to be written in this language. I think that's just a super fitting for fine-grained sediments that we're dealing with. And Jürgen could show us in some of his flume experiments that despite the very fine-grained nature, we also have a sorting and a contrast in sorting. For example, we have ripple flows like he shows right here with those black arrows. These ripples, maybe as you have, if they're not compacted yet, if they're being deposited, not compacted yet, they still show up in the cross section. However, if you compact it, they appear to be just horizontal layers. Hence, the very simple matter that we used to think of those laminated shales. So what is the origin of these laminations? And is it suspension settling, like you see these horizontal layers right here? This is the flume samples. Or are there ripple laminations? And it looks like, if you look very closely, you see this is 1 millimeter, this a scale right here. You can see very distinct sedimentologic structures right in here. So once you take a cross-section of this whole sediment, right here you can see some of the cross-bedding that is visible in here, and you compact it to 0% porosity. Basically, it all looks laminated. So these are the typical core examples that you see, laminated shales. Maybe you have a little bit of a sorting of silt-sized layers. So you can see those either can be, these silt-sized layers can be either composed of calcitic grains or any kind of terrigenous sand grains, for example. And then you see right here in this picture right here, we actually see through the sorting, there is quite a bit of cross-bedding going on. So hence we had some kind of current deposit in this more distal setting. These are other type of examples. We actually have, like right here, we have layers of more darker, probably more the background sedimentation, and then maybe small turbidites that would come into the basin in form of these more silt, coarser grained grains. Over here, for example, we have actually current flows that are starting to come up with this scallop nature in this more background sedimentation of more the organic rich sediments. So we have quite a bit of variations throughout some of the cores, and of course these are the best examples I'm showing of different types of cores, but that's maybe what you want to look for. So are these really ripples and shales? For example, Schieber and Southard early on show that the geometries of the ripples are similar to those produced by the sandy sediments. Right in here, you see they have just a very similar shape, and then your ripple laminations right in here. Very, very fine grained. I hope your screens are showing that it shows up well enough. And these can, of course, contain up to 90% volume percent of water. So think about it, when it gets compacted, it probably shows up just like a lamination. So I actually have been studying some modern mudrocks because I've been curious about different the processes that are forming these sediments. Are these sea level fluctuations, climate fluctuations, or just contour currents or anything like that? And I've been looking at the Cariaco Basin. I just wanted to show you one of the mudrocks that I've found is very characteristic and very similar to our different mudrock settings. And we can see right here we have these same layers that are more calcite dominated. These are more shale dominated, with more argillaceous sediments, very, very extremely fine-grained laminations throughout this interval right here. Actually see maybe a little bit of bioturbation in here. The reason why this is so curved is because the sediment is basically fairly unconsolidated mud, and so when you pull up the core barrel, that you just pull up some of the sides with it, so don't be confused by that. But look in the middle right here, we actually have some disturbances, maybe some ripple laminations. So at this point here, we have about 80% porosity. If you compact it, what happens? It's just your laminated sediment, right? It's just what you see. But you think, you know, when it was deposited, you had all these very fine-grained laminations, and actually a lot of these originated from biennial episodes where you had more shedding of winter and summer episodes, as some of researchers working on IODP cores have demonstrated. So there's so much information in these very young sediments. They're Pleistocene sediments, Holocene to Pleistocene sediments, that we can check out and then make some interpretation and inferences to our own shale basins. So I think this is pretty cool. What we also see oftentimes are these lenticular fabric examples right in here. And I see that in the Haynesville. I studied the Haynesville and the Eagle Ford extensively. But this one here, for example, is from Jürgen Schieber in Shale in India. And he was curious how these formed. And he came up also with his flume transport that maybe these lenticular fabrics formed through transport of lithoclasts, basically rip-up clasts that were transported through some current flow and then deposited down the road and then buried, and you ended up with this type of lenticular fabric. That's basically an intercalation of these squished glass, organics, shales. And why is this important? Why is this important to know? Because depending on what type of floccules you have, it has actually an effect on your porosity. So here, for example, right here, you have the settling of these loose floccules. You see those? When you compact it, there's basically no porosity left. However, if you have some of the lenticular settings where you have like maybe a larger or different grain sizes and you compact those, you actually can see you still have some porosity in these settings. Why is that important? You want to know, you want to frack into these more porous type sediments when you are like exploring for oil and gas in these unconventional reservoirs. So here's an example. This one down here, you see a really nice difference between the bedload floccules. It's more a little bit coarser grained. It's a lot more fluffy, and then these loose flocks here, the fluffy flocks, that settle and they collapse, and you kind of see that it's a lot less porosity into those than maybe the current deposited bedload floccules. So we can see here, for example, in the Haynesville, depending on where you are in the on the shelf, you're more closer, more proximal, or you're more distal. This one here, for example, I'm going to show you some examples from our study. We are core observations near carbonate platforms, and we can see that a lot of our shale plays are surrounded by carbonate platforms or very close to carbonate platforms, be it the Barnett, the Bakken, the Haynesville, the Eagle Ford, and a lot of other shales. Even the Marcellus has a little bit of carbonate influence. But if we are close to the carbonate platforms, we oftentimes see a calcareous base. And then the prevalent conditions usually go back to these massive facies here in this dark blue. Oftentimes they're laminated. And then you have episodic events. And you know, how did they form? Did they form through storms? Did they form through debris flows? And oftentimes you have like friable intervals, like I've shown you before in the course. So I'm going to show you some facies examples, and I want you to pay good attention because there will be a test at the end. We won't grade you, no worries. So here, for example, is these are thin sections of a core that's close to the carbonate platforms in the Haynesville Basin, but this is more the massive facies that you can see here. It's pretty structureless except for these shell fragments right in here that are probably inoceramide fragments. Then you have some little silt-sized grains. Maybe some of them are globigerinids. It might be a little bit too big in this example right here. But sometimes you also have the massive facies, can be actually having some bioturbation or some sorting of grain sizes right here. So you have finer grains and coarser grains where you actually might have had a little bit of a current in the basin right here. Of course, all these white shells right here, maybe inoceramide or brachiopod shells or ammonite shells. Then we have the episodic events. How do we know? Well, you can see it. Hey, it's looking at something in your core and you can see something. It's fantastic. Look at these beautiful inoceramide. I'm sorry, it's an inoceramide grave, but this must have been a flow. You can see how you have a depression in here from this flow in this background, organic-rich background sediments. Over here, we actually see some cross-bedding right in here if you look closely, and also the sorting of the grain sizes. In this one here also, we have finer grains right in here, coarser grained right in here, in this part of the thin section photomicrograph. So you see a lot of different grain size variations from very coarse grained shells or clasts that was maybe just point sourced from the carbonate platform that were shed into the basin, to very fine-grained episodic events that dislodged maybe some of the carbonate muds from the platform, or right here that looks like more like a skeletal fragment, maybe a crinoid fragment. A lot of these are crinoid fragments that were shed from the carbonate platform. Same over here, we have over this erosive base, we actually have stromatoporoids, we have some mud clasts. Down here we have stromatoporoids, bryozoans, clasts that were shed from the carbonate platforms. Over here we can see actually water escape features along these white arrows, and an erosive base. So very fine contrast, low contrast, maybe mud clasts that are deposited in the background mud. It's sometimes very hard to identify what you're actually looking at. You also can actually see maybe a bypass surface with a traction carpet where you have these coarser grained sediments that are flowing into the basin. Then we have cross stratification. All of these are from the Haynesville, and you can see it's very hard to see. You need a lot of imagination. Maybe you actually had a burrow that later on disrupted the cross stratification right here. If you don't have a lot of sediment contrasts of finer and coarser grain, that could be a problem to identify some of the cross stratification. You see here it's pretty easy, whereas up there it's not that easy to identify any of those. Right in here, again, we have some of the cross stratification right in this lower part of this thin section. Here might have been a burrow right in here, and then more cross stratification that then was later disrupted by the burrows. So all of these are thin section photomicrographs. This one here is actually a core photograph. It's polished core. It's not that easy to identify, and if you just take a quick glance at it, you will say, oh, it's just massive, but you really have to look very hard to identify it. And if you take my class, you can actually take the sample and identify it for yourself. So these are beautiful cross stratification samples from the Eagle Ford, and them probably was deposited maybe a little bit shallower, maybe a little less shallow. There's a big controversy going on, but I'm not getting involved in that right now. I wanted to show you these beautiful examples right here from Malaysia and Garcia. It's a beautiful poster. Check it out on APG Search and Discovery. And we can see here we have a lot of intercalation of more calcitic-rich intervals right in here, and then more marl layers, marly layers, or shaly layers in this in these dark layers right in here. You can see very sharp surfaces in here. We have nice stratification, cross stratification right in there. We have erosional surfaces in here. Just a lot of different sedimentologic features that are visible in these beautiful cores. Not only do we see these more finer scaled cross stratification, but we also see oscillation ripples right here with this red arrow, like you can see here. Maybe these were like storm layers that were deposited. Over here, there are big interclasts that probably came down in a debris flow. So you're thinking for yourself, well, is it more distal? Is it more proximal? What do you think where these coming from? I mean, think about the transport of these sediments. If it's coarser grain, they're probably more proximal. If it's finer grain, more distal. However, if you have more cross stratification, very small scale storm cross stratification or storm layers, it's probably more proximal. So this is a beautiful depositional environment picture from Malaysia and Garcia. Of course, this is very oversteepened right here, but you can see here some of the facies show maybe some bottom currents. Maybe this one here is composed like we saw before, right down here, these undulated beds, the oscillation ripples. Maybe there's storm deposits by major storms right in here. And then as we go down the depositional profile, we can see facies like turbidites, and then we get into the more pelagic suspension deposits. So you have all different types of sedimentologic features depending on where you are on the shelf, whether you are in the middle, more like on the slope, whether you're closer, maybe in little depressions, or in the very deep realm, the pelagic realm, where you have mostly suspension deposits, but these suspension deposits also can be disrupted by turbidites and debris flows. But you can see how the facies becomes a lot a lot darker and a lot finer grained as we go into the deeper settings, deeper in the setting environments. So why do you want to know that? Why do you want to know where you are? Which facies you are in, where you are with the depositional settings and where you're in. I mean, it's really important. Maybe your engineer will tell you, oh, it's just all about lithology. Of course it is, but you want to know why and where it is. So think about when you're starting to set your best frac interval stratigraphically. Would you do it into one of these facies or more into the dark facies? Would you look in the lithology? Right here you can see this is probably pretty calcite rich, or it could be also maybe silica rich. These are the facies that the ones that have more calcite and silica will frack more easily. So I will tell you in my class how to identify those and actually look at those. So in a summary, I wanted to hopefully I demonstrated to you that the mudrocks, the sedimentology in mudrocks are not just layer cake. You get some suspension settling of marine snow. They're little floccules that you will see, and they get squished, and you will get some of the laminations. But also the sedimentary structures will show you ripple laminations. You saw some of the planar laminations, load structures. You have the mass flows and debris flows. And then oftentimes, if you're a little bit closer, you have these episodic events. So you can have all of the coarser grained clastic sedimentary structures that you have in those very fine-grained environments. But you just have to look harder. So next I'm going to show you a little questionnaire. And this would be like an exercise, for example, of the sedimentology. And I'm going, if you look at closely at these beautiful facies types, I wanted you to check which one of these facies, or think about which one of these facies would be more proximal to distal. So unfortunately, we couldn't set up the poll in a way so you can actually vote on it. But the questions number 2 and questions number 3, there will be a poll after I get out of my presentation. So, for example, I would like you to identify the facies types and label from proximal to distal, 1 through 4. So we don't have the poll now, but you just think about it. You can label it in your head. I'll wait just a few more seconds before I give you the answer. Or if it's my answer, who knows? So you would think that this one here, right, is more proximal because it's has a lot more cross-bedding and a lot more sedimentary structures that maybe we actually had some storm or wave influence. Now this one here could be anywhere, really. This is a biotubation. You see a lot of biotubation in that. Usually when you have a lot of biotubation, it's more proximal, but you also could have that more distal, in a more distal setting. Now this was pretty clear, right? That's probably the most distal one. And this one could be fairly proximal, but probably a little bit more distal because you don't have very, not that huge of sedimentary structures, and you have very fine-grained silt and shale. So now I want you to see, you have these numbers A, B, C, D. Which facies do you think would be most conducive to fracking? Maybe just take a note. And then which facies A through D appears to have the highest TOC and why? You just take a vote and take a note which one of these facies, A, B, C, or D, and then we can have a poll. So I wanted to thank you so much for your attention, and I'm ready for my questions now. Thanks so much for attending the webinar.
Thanks, Ursula. It looks like we've got some votes coming in now on the poll, so we'll be seeing what the majority of the audience thinks, and then hopefully you'll give us your answer. I think we've got most people are almost decided here. We've got a few more votes coming in. So it looks like most of you voted on C. Would you like to comment, Ursula?
On C, but yeah, on number 2 and C, yes, that's right, that's correct. Because the reason why is because we have a lot more calcite, so you don't have a it's very conducive for fracking these more layer caked or these sediments that are intercalated or intercalated marl and calcite. How about number 3?
Now we'll start the second poll.
Oh.
So everyone has a chance to vote here. Which facies appears to have the highest TOC? We have some answers coming in now. You have to use your collective memory to remember what those 4 samples look like. Looks like almost everyone's voted. It's still tallying a few last-minute votes, people that are making a quick decision. Okay, so the majority have voted that B is the one that has the highest TOC.
Yeah, that's pretty obvious. However, it could also be any of the other ones. Believe it or not. Probably the highest TOC is the B, and because it's most anoxic, it has the most shale in it. It's less diluted than any of the other samples right here. Or I'll share my webcam. Here you can see me again. So I think usually that's what we go for, and that's usually what it is. Any questions from the audience?
Great. So audience members, you are muted, so the way you can ask your questions is to pose your questions in the question feature of GoToWebinar. Hopefully some of you may have some questions. We have a good number of people on the phone today. And while we're waiting for some questions to come in, I think, Ursula, you mentioned that there was some controversy about the Eagleford that you didn't go into, something about the timing of the deposition. Would you elaborate on that a little bit?
Yeah, it's interesting. There's so the one camp over at Texas A&M University, it's just like the Texas feud. They Art Donovan and Mike Pope, they think it's more shallower water deposits because of the sedimentary structures. The problem is that there are no organisms that show up that could actually corroborate the shallow water deposition. Bob Laux and Steve Ruppel at the Bureau of Economic Geology and Greg Fribourg, they think it's deeper water or deeper shelf deposits. And they attribute a lot of the sedimentological features to be related to bottom currents and below storm wave-based currents. So you have and there are not one single organism that would corroborate the shallow water environment, but there are some forums that might be there to corroborate more the shallow water, and there might be no, the controversy is still out, so I'm not getting involved in that. Say either or. Did we get any questions? Let's see.
Definitely some good arguments for either side. Yeah, just reminding our listeners that they can pose their questions in the question feature of the webinar. And for those of you who are in attendance today for the webinar, you will later today receive a link to the recording of this webinar. We'll have it posted on SCA's website. And there will be an evaluation form. We'd love to have your feedback about this, and a link to any details related to registration for Ursula's course. The course on, it's a workshop, a core workshop on sedimentologic and stratigraphic assessment of organic rich mudrocks that's in January. We have had some feedback from one of our listeners that there's no K in fracking. So that's also a good controversy in our business.
Good, good. I wanted to tell you a little bit more about the course. We're going to be just 2 days of lectures and exercises in the classroom. And then we have 1 day in the core workshop, in the core repository of the Bureau of Economic Geology in Houston. And I will show you cores from the Eagle Ford, the Haynesville, the Barnett, and the Woodford Shale. So you can, the highlights of all of these, you can see all of these cores at once, and you can compare and contrast those, the different cores. And if you're interested, please sign up in January. I would love to show you some of those features that I showed you today.
It's always better to see it in person. This virtual technology is great, but in person is even better. We have one question. As for the composition of the marine shale, do you think feldspar is a detrital indicator?
Detrital indicator?
Yes, the presence of feldspar.
Well, feldspar can be, I've seen feldspar in both ways, either transported in with some of the more terrigenous sediments, but also diagenetic feldspar that has been precipitated in some of the burrows. So it's both of it. Great. So it's really not an indicator. I would not put too much emphasis on it. It's a very minor element too, in most of the shale plays that I have seen. Okay, very good.
Lots of good feedback about the figures that you've included in your presentation. Does the proportion of kaolinite indicate the depositional environment?
Yeah, kaolinite it could be a problem for you, especially when you're fracking, and it's usually a little bit closer to your source, a little bit more proximal. I would not. I would really try to identify if you have a lot of kaolinite present. It just depends on where your terrigenous source comes from.
Excellent. Again, some good feedback on the presentation, and we want to remind our viewers that this is really just a sample of the types of material that you can cover in a multi-day workshop. So it's certainly not all-encompassing, but we do appreciate your feedback today on how powerful this material can be, and it's really great to be able to look at the cores and touch them and see it all in person as well. So right. I think that's...
And ask more questions.
And ask more questions, exactly. It's kind of hard going through this virtual context, but we do appreciate everyone's participation today. We will be sending out links to this recording, and we look forward to having your feedback. One more question. Your thin sections, are they reflective of the heterogeneity that exists in these types of reservoirs? Can you see that in the thin section?
Yes, yes. And you can see you can in the thin section, and then hopefully in the SEM you can see the different minerals. You can see the different fabrics that are in there. You can, in the thin sections, you always can see some of the organic flakes, the shales. You can see the calcitic or silicious sediments, different mineral types. You can identify. You can see burrows. Definitely, you need to make a thin section to really, at the least, to really see what's going on. And of course, you need to use your geochemistry to identify your mineralogical composition, like XRF analysis. So there's a lot more involved, of course, to determine what is going on with your shales. But as a first recourse, thin sections show very nicely what type of minerals and sedimentary structures you have.
Great. Well, I think that's all the questions that we have today. So we appreciate everyone's time. Thank you very much for the webinar, Ursula, and we look forward to getting everyone's feedback, and hopefully some people will be interested in joining us in the workshop next January. Thanks very much.
Thank you so much. Thanks, Houston. Thanks, Houston and Susan and SCA. Thank you.
Thank you very much.